Lecture 4 of Week 4. This week we're going to learn about photogrammetry. Additionally, I'd like you to watch the videos under the lecture portion on the Canvas Week 4 homepage. And I will be discussing various photogrammetry techniques, going over a case study, demonstrate how to use photogrammetry software, and then later in Week 5, I will talk about plane and ortho rectification of imagery and go over more quick case studies. If you need online help for photogrammetry, or if you'd like to research more than this lecture has to offer, then I suggest and recommend checking out American Society for Photogrammetry and Remote Sensing. The acronym is ASPRS. You can use search engines like Google, YouTube, reference the lecture notes, and then the required textbook. Photogrammetry is derived from the three Greek words photos, which means light, gramma means something drawn or written, and then metron means to measure. And so photogrammetry, by definition, is the art and science and technology of obtaining reliable information about physical objects and the environment through the process of recording, measuring, and interpreting photographic images and patterns of electromagnetic radiant imagery and other phenomena. American Society of Photogrammetry, that was 1980. So photogrammetry can digitize reality, such as this urban area. It involves capturing photos and potentially geospatial data and processing it with specialized software. The software will convert the images and their geolocation data into 2D or 3D data, including flat maps, orthomosaics, or 3D models, point clouds. Photogrammetry can be completed with multiple image capture devices, ranging from satellites to drones to mobile phones. The software to process these images can be desktop or cloud-based. Pix4D is an example, and it currently offers, 10 products that process images for photogrammetric outputs, including 2D maps, digital surface models, digital terrain models, radiometric multispectral maps, and more. And having these outputs means you can get an overview of an object or location rather than having to analyze hundreds of thousands of photos. Thanks to how this processing works, you can also measure volumes or distances, make annotations, and and share analysis via PDF reports or shared links. So there's many uses for photogrammetry. Topographic mapping is one of the earliest and still used. It varies in scale from large to small. It's used in private engineering and surveying forms. It's used in planning and designing highways, railroads, rapid transit systems, bridges, pipelines, aqueducts, and so on. And so orthophotos and digital elevation models, which I will call DEMs, replaced traditional topographic maps. Valuable tool in land surveying as the base map for relocating existing property boundaries, planning ground surveys through stereoscopic viewing. So this is a use case example. These are the Faroe Islands, and they're a set of islands in the Atlantic Ocean. There are 18 islands in the chain with 120 urban areas. The Faroese Environment Agency was tasked with tracking and mapping the changes on these islands, with a focus on tracking urban development and changes to the coastline. And so they decided to use photogrammetry to do such. However, being in the middle of the Atlantic, aerial mapping of the island is rare and difficult. Since 2017, the Faroese has collected 117,130 images at a rate of roughly 30,000 per year. So that's a lot. There are only 6 employees to carry out all of the responsibilities of a governmental agency. 3 work on land with surveying and mapping, while the other 3 work on nautical charts for ships and ferries. In 2015, the Faroese Environmental Agency chose to work with drones instead of planes. When they started using drones for mapping, they researched the strengths of drone photogrammetry. Part of the appeal of this is that the maps could generate orthophotos with less effort and strain than, airplane-based photogrammetry. As for selecting the right drone mapping software with a large-scale project, the power of the Pix4D Matic is most suitable for them, and so they use that software and produce an accurate Faroe Island map. And why drone mapping is the best choice for them? Well, it's a tiny island with just 31 inhabitants. However, the last time the island was mapped was in 2009. It was long overdue for an up-to-date survey. Several significant challenges are present with aerial mapping remote locations. The islands have mountainous terrain with strong winds, so that makes it more difficult for planes. The Faroe Islands' weather is notoriously unpredictable. Airplanes struggle to penetrate the cloud cover, and the risks of flying beneath the clouds with such rough terrain mean it is very difficult to fly safely for aerial mapping. So the benefit of the drone is already clear. They can be deployed with less notice and planning than a plane, and take advantage of short gaps in favorable weather windows. Furthermore, the drones fly below the clouds, which is an obvious advantage because of their visibility, and it's not prevented by cloud cover. And then continuous gray skies cause a consistent light that does not change dramatically, which is ideal for photogrammetry data collection. However, fixed wing drones do sometimes struggle due to the uneven terrain, making it hard to find appropriate locations to take off and land. So there are a few setbacks. So land surveying in a remote island, when the environmental agency's pilot flew the drone, the data collection mission was separated into 3 flights that gathered a total of 1,997 images. This careful flight planning can save pilots lots of time when flying large or complicated sites. Luckily, the wind was gentle that day. There was some turbulence and difficulty from the layout of the terrain, although luckily, the Faroese has some flat spaces from which the EBX could take off and land safely. The data was then processed in the program Pix4Dmatic, taking just over 10 hours to crunch the whole data set. The final map was then edited and annotated, and to add important details including coastlines, housing, which included road names and addresses, pastures and agricultural plots. This map is provided as an open access resource for anyone to download. Although it is in Danish, open maps are a useful resource, enabling everyone to better understand the lay of the land. So there are other uses of photogrammetry. One is crime scene recreation. Another is accident scene response. It's often useful to have an accurate 3D reconstruction of an accident or a crime scene, especially in cases where position, distance, and perspective are important. In this mock-up of a crime scene in a hotel room on the right, a variety of objects of evidence are identified in the point cloud relative to each other and the entire room in 3D. It was created using a Trimble X7 3D laser scanning system combined with Trimble perspective field. From this angle, the point cloud reveals the larger apartment space, helping to establish the proximity of evidence and the activity. A point cloud can be used for a complete perspective of a crime scene from different viewpoints. Analog photogrammetry consisted of first-generation stereo plotters in 2 types: direct optical projection instruments and then instruments with mechanical or optical mechanical projection. It creates true 3D stereo model by projecting transparency images through lenses. The model formed by intersections of light rays, LNR, which we will call L&R. Direct project of light rays by mechanical or optical mechanical is aimed in this analog photogrammetry. And then the output from this process was topographic maps. So analytical photogrammetry is a rigorous mathematical calculation. It rigorously accounts for any tilts that exist in the photos, the solution of large complex systems of redundant equations by least squares. The 3D models are mathematically created, as in previous methods that I just described in the last slide. So measurements are made in 2D images, and then the output are digital terrain model generated orthophoto production, digital photo rectification, and areotriangulation. And then lastly is the digital photogrammetry era. So digital image stored and processed on a computer and could be scanned from photographs or directly captured by digital camera. So it's the most advanced form of photogrammetry. Each picture element, pixel, which we've learned about in previous weeks, has its known position and measured intensity value. So X and Y photos coordinate pair must be related to the principal point as the origin. So photogrammetry is an engineering discipline. Today's photogrammetry is heavily dependent on software and hardware. The ever-increasing use of computers and software has a great impact on developments from analog to analytical and then now digital methods. Photogrammetry requires certain skills, techniques. We have to learn about those techniques and judgments to be made for taking reliable measurements by the photogrammetrists and experienced interpreters. We are using the single vertical aerial photography sometimes, but mainly many other times we use stereoscopic aerial photographs, which means it's multiple photographs with overlapping areas. So what can photogrammetry do? It's a single vertical aerial are used many times, but in large projects, sometimes we use stereoscopic photographs. So with single vertical aerial photographs on the left in the blue square, we can figure out the distance between objects, the area perimeter of a polygon, we can map objects, etc. But with stereoscopic aerial photos on the right in red, in the bottom right, means you have two photos that have an overlapping region. And so then we can figure out the planimetric, but also the height. We can create a 3D model. The best example of a 3D model is the DEM, digital elevation model. 2D versus 3D. So we have to obtain accurate photographs and the latest photographs. So we have to see that our photographs are highly accurate and they are the latest and representing the most accurate reality. So we get the latest information. This diagram is showing how a 3D image is imaged with the help of a camera, photographic camera, and we are taking the two images of this from two different angles and carry out a 3D model. So 3D to 2D and then to 3D in our computer environment, or the determination of the coordinates of the various points in terms of X, Y, and Z. But we can also do the reverse process if we have a two-dimensional photograph of the same object. We recreate the same geometry as it was taking these photographs. So the middle step, what you see here, is recreating the geometry in the lab with the help of the devices and software. And those 2D images are converted into a 3D image. So let's talk about the principal point. The principal point is the center of the photo. And then the focal length refers to the optical distance in millimeters between the camera's sensor and the point in the lens where light rays converge. The focal length determines the angle of a view and the magnification. A smaller number, a short focal length, means a wider field of view and lower magnification, so the camera can capture more of the scene. In photogrammetry, you will usually have a fixed focal length. The lens focal length determines magnification and the field of view, how much of the scene can be captured. That's the focal length. So triangulation works by identifying common points in an overlapping picture and determining their positions in 3D space relative to the known positions of the camera. Having overlapping images is key to photogrammetry. By identifying the same points in multiple images and taking it into account parameters like the camera's position and orientation for each photograph, its focal length, lens distortion, and other variables, it is possible to determine where those points were located in 3D space. This is called triangulation. When one point is identified in at least two pictures taken from different known locations, we can draw imaginary lines, like you see in this image, from the two camera positions in the direction of that point. We then mathematically determine where the lines intersect. The converging lines give us the XYZ coordinates of the targeted point. And with enough points, we can construct a model of the scene. Human beings actually do this exact same thing intuitively. We are essentially walking around with two small cameras in our heads, spaced apart slightly to help us to perceive depth and distance. So the film plane, the plane inside any camera with a lens which the film or digital sensor is located. In a properly designed camera, the film plane is the same plane as the focal plane. The distance of the film plane varies based on the focal length of the lens. Principal distance, the distance between the lens plane and the image plane. The camera's distance setting should be set equal to the principal distance. So methods to set principal distance, you can do autofocusing, which focuses with participant standing in the middle of the field of view. And then you can also turn off that autofocus. So you could do it manually, which measures the distance from the camera to the plane of motion. And you set this manually yourself on the lens. Calibration of imaging systems. So calibrating must be used to ensure that the image coordinates are correctly scaled to size. The aim is the determination of parameters of interior orientation plus additional parameters. And then elements of interior orientation, so the position of perspective center with respect to visual markers, the coordinates of the visual marks, the calibrated focal length of the camera, the radial and discentering distortion of the lens assembly, and then image quality measures such as resolution. So there are different methods of calibration. The manual method is to use this formula. S equals actual length over digitized length. And so 2D systems with one camera, you use a calibrated ruler or surveyor's rod placed in the participant's plane of motion. And then you scaling factors, which can be determined for both directions. Method of calibration, multi-camera systems establish a series of control points. For 2D analyses, at least 4 non-collinear points are required, but for 3D analyses, at least 6 non-coplanar locations on a 3D structure are required. So the accuracy of calibration, most accurate calibrations are seen when the control points are evenly distributed across the control region. So the accuracy of 3-dimensional calibration increases as the number of control points increase from 8 to, say, 24. So at 16 points, the system starts to stabilize. Large errors can be seen at the corner of the calibration frame. So resolution in remote sensing is the ability of a sensor to distinguish or resolve objects that are physically near or spectrally similar to other adjacent objects. DPI constitutes the resolution in which the original frame or film was scanned as well as exported digitally. DPI resolution of an image will only be as good as the resolution in which the digital image was first scanned. For example, if the original frame is scanned at 600 DPI, exporting a digital image at 1000 DPI of the same frame will look no better than it would be at exporting 600 DPI. Resolution in terms of spatial accuracy is generally described as 1 meter resolution or 3 meter resolution. The smaller the denomination is, the higher the quality and spatial accuracy. For example, most current NAIP imagery is collected at 1 meter resolution, which provides plenty of clarity to view buildings and other structures as opposed to older NAIP imagery, which is generally closer to a 2 meter resolution. So scaling in photogrammetry is you're taking the height of object from relief displacement. So an example, if you have 1-inch football field on a photo and you know the football field is 100 yards, so you can scale that so it is 1 to 3600. So a formula for scale is scale equals camera focal length, which is F, divided by flying height above ground, H. So 12 in focal length lens divided by 1200 foot flight altitude would give you a scale of 1 to 1200. And we're going to go over this in lab as well. Relief displacement is important, so the lower the elevation of an object, the more it will be displaced toward the principal point. This effect is called relief displacement. In the object on the right, towers A and B are equally high, but placed at different distances from the nadir point, thus have different relief displacements. The single tower depicted beneath nadir point has no relief displacement. So the relief displacement method, the lower the elevation of an object, the more it will be displaced toward the principal point. Like I said in the last slide, this effect is called relief displacement. So let's talk about the actual formula. So you have height of an object equals the length of displaced object on the photo times the flying height above the surface divided by the radial distance from principal point to displaced image point. And again, we're going to go over this in lab, so it'll make more sense then as well. So you can also determine the height from a shadow. So the height from shadow includes the length of shadow and sun elevations angle, which we are going to look up. Some problems with this is due to if you have uneven ground or a leaning object or shadows not from the top, ground cover showing shadow, things of that nature. But the equation for this is height is equal to length of shadow times the tangent of the sun's elevation angle, which we can look up online for a specific date and time. Parallax, apparent change in position caused by apparent change in viewing angle. We can use the principal parallax to determine the height of an object. You can use a parallax bar, or a stereometer to measure the difference of parallax between any 2 points more accurately or precisely. The bar has a micrometer screw with 2 perpendicular ops attached in the vertical direction. One is glass graticule and the other is a floating mark, which you could see down here in the bottom right image. Parallax differences are measured with those floating marks. The separation of those marks can be varied with the help of a micrometer screw, which gives reading up to 1/100th micrometer. So let's take a look more closely at scaling in photogrammetry. So this is going to be under lecture to learn more about scale and resolution for this week. Thanks.